which is the NEXTAEC. It's a project coordinated by DTU, Technical University of Denmark, and more precisely by Jens Oluf Jensen. I hope I make good pronunciation. And Jens is professor at the Department of Energy Conversion and Storage at DTU. So Jens, the floor is yours.
Thank you very much. Now I've tried to share my slides. I hope you can all see them. And thank you for the invitation to take part in this nice workshop. It has been a pleasure this morning to hear all these nice overviews, and they have also introduced some of the things that I'm talking about. So it's been a good primer. I hope some of the audience have been there in the morning as well. But I'm the coordinator of...
Jens,
yes?
if everybody is I don't see your screen. Is it the same for the other?
Yeah, exactly.
I'll try sharing again. It says it has been paused. I'll just stop and start again.
So it's not working.
Is it working now? Now it says you're sharing.
Now it's okay. It's fine.
Very good. Thank you.
Much better. Okay. Yeah. Sometimes it's paused. I don't know what causes that. I saw that the other day as well. So, but let me know if it drops out, and I'll go in and out again. What I was about to say is that I'm the coordinator of the Horizon 2020 project, NEXTAEC, which stands for Materials for Next Generation Alkaline Electrolyzers. And it is running for 4 years, starting in April 2020, and running for 4 years from then. It's a call called Materials for Non-Battery Energy Storage. So it's not part of the joint undertaking, but another branch of the large system. It's funded by around 4.5 million euro altogether. We have a number of partners, 10 altogether, and some of them Lund University in Sweden, University of Patras in Greece, and ourselves, Technical University of Denmark, and then a Korean partner, Korea Institute of Science and Technology. And these are the membrane partners developing these new membranes that I'll talk about in a minute. We also have Blue Well Technologies that introduced themselves as a fuel cell company this morning by Hans-O Euler. He mentioned also they have a side activity with electrolyzers, but they're basically a membrane specialist and producer. So they're scaling up the membranes that we are developing. Then we have some electrode partners, and these are the main roles, and some of the partners do different things. But the main electrode developers are DLR, the German Aerospace Center, and the Catholic University of Louvain in Belgium, both very experienced in electrodes. Then we have the Jülich Research Center and University of Chemistry and Technology in Prague for the systematic testing of all the nonsense that come out of our labs. And finally, everything will be merged into a NEL electrolyzer stack for test and demonstration in the end. Right, the background for all this has been outlined to a large extent today. That makes it easy that we have a tremendous need for electrolysis, and the production capacity, not for hydrogen, but already for the electrolyzers, must be stepped up significantly in the coming years if we should meet these targets. Today it's said to be below a gigawatt, but that is certainly changing. I know that many of the electrolyzer producers are extending their production capacities very fast now. So if we should have an affordable and scalable to this terawatt range of electrolyzers, we should look at the different technologies, the main technologies we have around. And that's of course the traditional alkaline, or the alkaline in general, traditional or modern. And we have the PEM electrolyzer and the solid electrolyzers coming up too. We can say that the PEM and alkaline, they are marketed and they are mature, very mature or quite mature. They are also proven over the years robust. The PEM electrolyzer has become quite robust too. The downside of the alkaline, which is the least expensive, it's perhaps not exactly cheap, but the cost is moderate, is this low power density. You need to buy a lot of it. And that's the strong side of the PEM electrolyzer. It's so compact with a very high power density. So you don't need to buy a lot of it, so you can afford a higher price. The big problem here is the limited scalability. If we're going to these multi-gigawatt or even terawatts of electrolyzers, then the dependence of iridium will limit the application of the PEM electrolyzer. It is reduced all the time, the amount, but it is not eliminated. So we need something as well as the PEM electrolyzer. The solid oxide is probably not limited in materials, but it needs some upsizing. We still only see quite small electrodes or cells. So that is something that the industry is working with. So the question is whether it's ready for the first big wave of electrolyzers. Probably not. So we are looking at the two others, and that makes it very important to do something with the alkaline system, and that's what we are targeting. So we believe that if we look at the problem with the PEM or the alkaline electrolyzer today, that's the low power density, which is actually a low current density at a reasonable voltage. So that's mainly a matter of internal resistance. And that boils down to the membrane, which is today a diaphragm, which actually works pretty well, but the internal resistance is higher than it should be. So if you can replace the membrane with a thin one, like the one we have in the PEM electrolyzer, and we can make porous three-dimensional electrodes like the ones we have in the PEM electrolyzer, there's no given physical reason why it should not perform like a PEM electrolyzer. So that's the basic idea that we're working with here. So the objective is to make such an electrolyzer and demonstrate PEM-like performance without the use of noble metals. That's one of the nice things with the alkaline system. We do not depend on noble metals for a catalyst. We have lots of nickel-based materials that are actually very active in the alkaline environment. So we'll develop membranes like that, and we will develop better electrodes, and then we will demonstrate everything in the electrolyzer after some upscaling, as I already mentioned. And that should be a fully scalable technology that can go to the multi-gigawatt or even terawatt scale eventually with this technology. And the more specific objective is for the membranes, we are going for conductivity that is beyond 0.1 Siemens per centimeter at 80 degrees. This is a membrane that will be fully immersed in potassium hydroxide. We are looking at different concentrations, but probably we're going to have quite a high concentration in the end. So that way it will be very similar to the known alkaline electrolyzers, just with a lower internal resistance. The electrodes we're working with both 2D and 3D. DLR has a very good technique for making electrodes on plates to provide catalytic layers, but we are going into the 3D regime and developing that by a variety of different processes for that. For the single cell, we have a target of 3 amperes per square centimeter at 2 volts. It's possible that it will be operated at a lower voltage that will be desirable for sure, but that's just an easy benchmark to see what is the current at 2 volts. And we'll demonstrate 5,000 hours with less than 10% degradation, either measured as a voltage increase or a current decrease. And for the stack demonstration, we are aiming at full size, which is 600 square centimeter. This is something that fits a suitable stack design that NEL already has. And it is, of course, not as large as the large alkaline electrolyzers, but with the higher current density, it is perhaps not likely that the cells will be that large. But this is a practical solution that we will work with. But let me go a little closer to what it's really all about in the technique. Our selling point for this project is the membrane concept that we're working with, and that's a so-called ion solvating membrane. The usual solution today, as we've heard about, is the porous diaphragm, which is almost exclusively, I think, the Zirfan materials from Agfa, which is working very well, but we would like to bring down the internal resistance. And they are also working on that. We've heard today, making it thinner, and that's of course a good way to go and a competing technology. But in many groups, the dream is to develop an anion exchange membrane with side chains that resembles that used in the PEM electrolyzer, just with cations immobilized on the side chains instead of anions. And they are typically, instead of sulfonic acid, it is a quaternary ammonium ion. These membranes, they behave very well these days. They have, in very recent years, obtained conductivity that is really high enough for excellent performance, but the stability is still an issue. And the big problem here is very often that the side chains are the weak part, so they break down fast. So our idea is to say we're going to do without these side chains. We're going to make a membrane by material that can just take up the electrolyte. You get a sort of gel-like structure. That's why it's called ion solvating. So it dissolves the ions and the water from the electrolyte inside. And that's exactly the same system that we've worked with for many, many years, also together with Danish Power Systems, now Blue World Technologies, that we met this morning, with the PBI, the polybenzimidazole polymer that is doped with phosphoric acid, and that is what they do at Blue World for fuel cells. Now we have started going the other way, dope it with potassium hydroxide instead, and then we get an equally good ion conductor, which we can use in the alkaline system. And we have already demonstrated this performance of 3 amperes at 2 volts, together with our partners DLR and Jülich, and that was published in the paper. That's a reference here below. I think you get the slides afterwards, so if you are interested in more details, you can see about that. The thing here is that we have not solved everything. We've shown that this is possible, but the durability is not good enough. These cells break down way too fast. So that's something we are addressing in the project, to try to find other ways. We were looking at PBI also, but other polymers that should be more stable. For the electrodes, as I mentioned already, we look at the 2-dimensional and 3-dimensional structures. Actually, the 2-dimensional structure is also 3-dimensional, but it's put on applied to the catalyst layer on a solid perforated nickel plate. But the 2- to 3-dimensional structures are often made on a foam, like you can see in this image, but there are many other ways to do that, and that's something we are exploring. It's a bit premature to present results for this yet, but that will certainly come later. And that's DLR in Germany and the Catholic University of Louvain in Belgium that are driving this. This figure is just from another paper that is completely disconnected from our project. It's from way before, but it's a nice overview of some of all the possibilities for non-noble materials for catalysts in both anode and cathode in the alkaline system. For the testing, we have Jülich and University of Chemistry and Technology Prague to play with our cells and materials. And then we will have upscaling by Blue World of the membrane, and the electrode makers will upscale the electrodes, and then NEL will have it all and put it into their stack. We will look into durability naturally, and also gas permeability. We believe this ion solvating concept will have a lower gas permeability because it's a much denser structure of the material. For the future challenges and gaps, well, we have a 0 gap configuration, so perhaps we have eliminated one gap. but there may be other gaps. We have demonstrated the PEM-like performance, but the durability is certainly not demonstrated yet, and that is what we really hope to do. We have an issue with polymers that are stable at high pH. They are generally very hydrophobic. We cannot get this electrolyte into a hydrophobic material. So we need to manipulate the hydrophobicity into hydrophilicity, either by modifying the structure or making something completely new. It can be blends. We know PPI works well. We're also working on stabilizing PPI. We understand pretty well what goes wrong, and that's several pathways for that, and we also have several partners. Then, of course, the application of catalyst on the three-dimensional materials by techniques developed for two-dimensional materials. That's also a challenge, but there are also, again, several techniques to choose in between. We'd also like to have a better understanding of what really happens with bubbles and bubble release and general transport effects in the catalyst layer. And then, of course, when we come up with something that really works, we should make sure that it can be produced in an affordable manner. Finally, before I thank you for your attention, I'd like to keep this attention a little longer and remind you that we have the International Conference on Electrolysis, which started in Copenhagen in 17, continued in Norway in 19, and it was supposed to continue in Colorado in the United States in 21 this summer, but for obvious reasons, we had to postpone it. So that'll be next summer in June at Colorado School of Mines, chaired by Brian Pivovar at NREL, and that'll be in 22, but we'll keep the name ICE 2021. So hope to see some of you over there, and then I will thank you for your attention with this somewhat provocative image that we use, that we have the line of development from the asbestos cloth over the thick porous diaphragm, the nanoporous AEM, and then the final, the hopefully non-porous membrane that we develop. We may see these components come out in another order at the end of the day, but this is how we see it at the moment. Thank you very much for your attention.
Thank you, Jens, for this nice straight to the point presentation. So I see no question, but I have two questions for you. So you address your project, I mean, the challenges of the alkaline electrolysis through the membrane. And I would like to know more about this ion solvating problem. You raised some durability issues, right?
Yes.
And what are the levers, the materials levers you foreseen to get rid of these durability issues?
Yes, we know that some polymeric materials are very stable and long-lasting in the alkaline solution. We know from the Zirfon membrane made from polysulfone and polyphenol sulfide, it lasts pretty long. So we know it is possible. But we also know that these materials are too hydrophobic as they are to take up the electrolyte. That's why the zirconia particles are added inside the pores. And that's a very smart way to do it by ACFA or FITO, where it was developed. But we have to make the polymer more hydrophilic, either by adding functionalization, functional groups, and so on, but in a way that it does not compromise the stability. And that's the balance, the delicate balance we are fighting against. I don't know if that answered your question. Yeah.
I understand that you are going to take some polymer from the market. You are not going to use organic chemistry to synthesize new.
No. We certainly are working in the lab. We are making polymers from scratch. When I say modifying, is that we just build it up in a new way. No, we do a lot of polymer chemistry in all the membrane groups.
Okay,
for sure. Mm-hmm.
Okay, that's it for me. Thank you again, Jens, for your presentation. I will need you. I will need you after for the workshop, so that you can share also your vision for your alkaline electrolysis, but potentially for other electrolysis technologies.